Hi guys, it's Kate, and I'm making this video to walk through a few examples of how to graph a given function and its derivative. This is an important skill that will come up time and again, and so it's really good to develop a system of exactly how to analyze these questions. Let's start with a basic one. Here's our function. It's the absolute value of x minus 1. Now, first things first, let's graph that function. It is identical to the absolute value of x, it's just shifted over to the right by 1 unit. There we go. Now, let's label important points here. We want to label our intercepts, so we do have a y-intercept at positive 1. We also have an x-intercept at positive 1. Let's set up the axes on which we'll graph our derivative. Now remember, the derivative is the slope of the tangent line at each particular point. And as luck would have it, our graph actually is a linear function, just two different lines pieced together. So the tangent line is the same or identical to this line for x less than 1. And then the tangent line on this side is the same as this line for x greater than 1. And the slope here along this line, let's talk about x less than 1 first, is going to be negative 1. So we want a function whose value is constantly negative 1, the slope of the tangent line, for all x less than 1. Now let's take a look at what's happening for x greater than 1. For all x greater than 1, the tangent line, which happens to be identical to this function, has a slope of positive 1. So we want a function that's constantly valued at positive 1 for all x greater than 1. Now the question is, what happens at 1? Well, what's the slope of the tangent line there? If we zoom in very closely, we see that the function looks something like this at that point. It has this weird little kink where the absolute value function switches direction. Now, if you're trying to challenge yourself to come up with a particular tangent line at that point, note that you could choose from an infinite number of options. There is no one single tangent line at that point. And then when we remember the definition of tangent line, we remember that it applies to only functions that are locally linear. That is, when we zoom in very, very close, the function itself looks like a straight line at that point. And in fact, this function does not, because no matter how closely we zoomed in here, we would see a kink, no matter how closely we got. It wouldn't be a straight line, there would always be that corner. And so, in fact, there is no derivative at x equals 1. So we put open circles at x equals 1. This means that the function is not differentiable there. It's really important to understand this. A lot of students come to me and they say, look, there are all these tangent lines that I could possibly draw, and I have to tell them, remember, the tangent line has to model the function's behavior at that particular point. The tangent line mimics the behavior of that function at that point, and the function itself has to be locally linear, and this is not. It doesn't have a single tangent line at that point, and so for that reason, the derivative function doesn't have a value at x equals 1. Let's try another example. Now our challenge is to graph this function and its derivative. This looks really challenging. Whenever you see something like this at first, one good step to start off with is to try to factor the numerator and the denominator. This is a great help. We see that the numerator and denominator share a common factor. We're going to take it one step further. Well, what does this mean about the function written in that format? It means that the function's graph looks just like x squared minus 5, but it has two holes, one of them where x equals positive 2, and one of them where x equals negative 2. This is a skill determining where holes exist in functions by factoring that you should have learned about in your pre-calculus class, but it's good to brush up on. So let's go ahead and graph the function. Not really drawn to scale, but this is basically what it looks like. Alright, let's also label that intercept. Alright, our next step is to draw the derivative of this function. First things first, we need to figure out where the zeros are going to be. Note that our parabola here switches direction right at x equals 0. So that's where our 0 is going to be. It goes from decreasing to increasing there, so the slope goes from negative to positive. Good notes to make on your drawing. So we note that it's going to go through the origin, and in class we noticed that for parabolas their derivative is going to be a linear function. So we want a linear function that's going to take on negative values over here, positive values over here, so it's going to be upward sloping. Now I've left two important points blank. What's going to happen at -2 and +2? Let's take a look at what the limit definition of the derivative at those points looks like. Note that both of them mention the actual function value at -2 or +2, depending on which derivative you're talking about. And in fact, the function doesn't exist there, so neither do the derivatives. I've written here that f is not differentiable at positive or -2. So there are going to be holes in the graph there. One at -2, one at x equals +2. Let's move on to one final example. All right, here's our function f. It is the absolute value of x to the 4th minus 9x squared plus 20 all over x squared minus 4. It's the exact same function that we had before, just absolute value of. So let's take a look. Our original graph of the function looked like this. It was that parabola with two holes in it, one at +2 and one at -2. Well now, remember what happens when you take the absolute value of something. Everywhere this function was positive, it's going to remain exactly the same. But anywhere it took on a negative function value, it is going to become a positive function value and essentially flip itself over the x-axis. So that's what our function f looks like. It's the yellow part. I'm going to label all my important points, that the holes are happening at x equals positive and -2, and that the vertex is happening at 5 now instead of -5. Now let's take a look at what the derivative should look like. I'm going to go ahead and label where those two holes occur. This is the original function's derivative. We know that the holes are still going to end up at x equals -2 and +2. Now, the function's derivative is exactly the same for the part of it that was identical to the original function. So right underneath -2, and also on the other side, just above +2, those are going to be plus or minus the square root of 5 if we're getting really technical about it. So far, in those particular places, right through here and right through here, because the function has not changed, the derivative has not changed. Now, of course, what happens at this particular point? Negative square root of 5 here and positive square root of 5 here. We have another kink, and like we talked about in the very first example, when we have a kink, that is a place where the function is not locally linear. In fact, it doesn't have a tangent line that mimics its behavior, and so it is not differentiable there. I've gone ahead and labeled those points and added in the holes to show that the function is not differentiable there. Now we've reached the part of the function that did that weird thing when we took the absolute value. It has been flipped over the x-axis because it was where the function took on negative values. Now they're positive. Well, let's take a look. The slopes of the tangent line here, where the function was decreasing, are now identical in magnitude to the slopes of the tangent line here, just opposite in sign. So where the function was decreasing, it's now increasing by exactly the same amount. And where the function had a 0 derivative, that is, it switched from decreasing to increasing, it now has a 0 derivative as it switches from increasing to decreasing. And we still have these problem children here where the function is not defined there. And so just as in the previous example, we know that the derivative does not exist there either. So let's start very slowly. We know that we still have this place where the function goes from increasing to decreasing, and so there's still going to be a place where the derivative equals 0 right here at x equals 0. Now, just like we said, by reflecting this part of the function over the x-axis. What used to be decreasing is now increasing by the exact same amount. The magnitude of the slope has not changed, only the sign. And so what used to lie under the x-axis on the derivative of the function's graph now is going to reflect over the x-axis and go right here. A couple things it's very important to note. Because the function does not exist at -2 and +2, it is still not differentiable here. It still has that hole that just got flipped over the x-axis. But again, this is capturing the fact, by reflecting it over the x-axis, this is capturing the fact that the magnitude or the number of the slope has not changed, just the sign. What was decreasing is now increasing. What was negative is now positive. We have taken this and reflected it over the x-axis. The same thing happens on this side. What was originally increasing here is now decreasing. And since we reflected all of the points over the x-axis, what was increasing is now decreasing by the exact same amount. It's only the sign that has changed and not the actual value of the slope of the tangent line. So what used to lie here above the x-axis, because it had positively sloped tangent lines, is now going to lie below the x-axis. Since we're switching just the sign of the slope of the tangent line, what we're doing is taking the function, the derivative of the function's graph, and flipping it over the x-axis, and it looks like the following. It's important to be clear with yourself that you understand that these two segments right here are identical to the original function's derivative, that all of a sudden, because of the kinks here and here, we now have a hole in the derivative of the function's graph at positive and negative square root of 5, because the function is not differentiable there, and that the only thing that has changed about the function through here, where we reflected it over the x-axis, is that the derivative of the function's graph has also been reflected over the x-axis. And so this is a graph of the function's derivative. If you have any questions at all, please don't hesitate to ask.